let phi be a homomorphism. With kernel H. Then the cosets H form what's called a factor group. And it's usually written this way. And whose binary operation defines the product AH BH of two cosets by choosing elements A and B from the cosets. And letting AH BH equal AB H like this. And now, one thing to remember, we were saying before, if you have a bunch of cosets, the cosets themselves don't form a subgroup, but this factor group is a group that consists of members, and the members are the cosets themselves. So in other words, the members of this group name that's marked like this, this almost looks like a division sign. That's kind of the way, it's almost like, looks like you're dividing, and it's called the factor group, but that could be a little bit deceiving because there's no division involved in anything. But again, this is a factor group, and these cosets themselves form a group. And again, they have this binary operation where like AH times BH. So if you're like multiplying these two members, these two cosets, then that's going to end up being defined by ABH. So again, we'll be working with this a little bit later. And let me just say some things. So this theorem states one, the cosets of H and actually, again, which in this case is the kernel of B, form a factor group. And it's also called, a lot of books call this a quotient group, aka quotient group. called that. So again, that's it. I'm just sort of restating what's up above. The cosets of H, in this case, where H is the kernel of phi, they form what's called this factor group. And the group operation is defined by AH, BH. Again, you can write it like I did up above, or just call it ABH. And then, yeah, so let's go on from there. And just have some more theorems. The map GH to phi G defined by mu of AH equals phi of A. So again, you have a map from the factor group to the group G. This is an isomorphism. And so let's just note a couple other things here. For a factor group, we need a homomorphism. B, we need the kernel which we call H. And we also need the cofactors. And then the cofactors or cosets H form the factor group. I guess I'm sort of restating things a few times here. And so let me take some examples here. And just want to show how you might add some stuff. So consider the map gamma from Z to Z5. Where this function is the remainder when M is divided by 5. And so again, we're looking now, let's say if we think of the kernel, so the kernel of this function gamma are going to be those values from z that produce 0. And so, of course, if you put 5 in, that's going to give us 0. If you put 10 in, that'll give us 0. So the kernel is going to be equal to 5z. In other words, that's going to be the set 0, 5, 10, 15, 20, 25, and forever and ever and ever. And so again, that's going to be the kernel, because if you put that into our function, if you put 0 in, 5 in, 10 in, that's going to just give you 0. And then so the cosets of 5z are, again, 5z. You can think of this as 0 plus 5z is going to give us, and I probably shouldn't, I sort of, it's a little bit misleading that I started at 0 here. This would actually go back into negative infinity. So then the cosets, first one would be like negative 10, negative 5, 0, 5, 10, 15, 20, and forever and ever. But I say I that's a little bit misleading the way I started here at 0. This would actually go back like into the negative 5, negative 10, negative 15, etc. So if we take 0 plus that set, we're going to get this. If we take 1 plus that set, we're going to get, let's say, negative 9, negative 4, 1, 6, 11, on forever and ever. If we add 2, we're going to get negative 8, negative 3, 2, 7, 12, etc. If we take 3, negative 7, negative 2, 3, 8, 13, etc. We add 4. That's going to be negative 6, negative 1, 4, 9, 14. And if we add 5, we're going to be repeating, huh? So these are going to be all the cosets. So these are all the possible cosets. And once again, you can see that they partition a group. You know, we get all the numbers. You can see negative 6 through negative 10. Or think of this way, 10, 9, 8, all the way up through all the integers. So this partitions a set. Like I said, you can see right away, if we added 5, it'll be the same as this coset. So these are all the cosets right here. And now the idea of this, so these cosets form a group. So these cosets form a group where you have like one of the members of the group is going to be 5z, 1 plus 5z, 2 plus 5z, 3 plus 5z, 4 plus 5z. And so those are the members of the group. And now, if you pick any element and add it to any element of another group, so let's say if we take, so let's just do an example. Let's say add 4 plus 5z to 3 plus 5z, we get, this will end up being 7. So that'll be 7 mod 5 is going to be 2. We get 2 plus 5z. So that's how we kind of work with the members of the group. You can like add the members together and you get another member of the group. And let me give another theorem here. Though, like I said, here where the operation is addition, though they usually just almost like show it as multiplication when you actually see it written. And so, so let me give you another theorem here. And this comes under the heading factor groups. From normal subgroups. And here's a theorem, let H be a subgroup of a group G. Then left coset multiplication is then left multiplication is well defined by the equation we mentioned before. Like I say, they kind of always show as multiplication no matter what the operation is. And so I'll write it the way this is the way we'd written it before. And then if and only if the left and right cosets coincide. So that AH equal HA for all A and G. So in other words, that this equation is going to be true if and only if the left and right cosets coincide. In other words, that they're equal, which again means, i.e., this is a normal subgroup. And we said a minute ago here, if in the case of if this came from the kernel, then it would be a normal subgroup. So that's why we could have that for the kernel before. But now this is extending a little bit farther, that if we have a normal subgroup, then this operation is still well defined as long as we have a normal subgroup. So these are equivalent conditions for a normal subgroup H of a group G. A lot of times they'll say the following, you'll see this in math a lot, the following are equivalent. And a lot of times they'll just put TFAE, the following are equivalent. And so number one, so again, if you want a normal, you want to test for a normal subgroup, one test you can use is if G inverse is in H for all G in G and H in H. That's one thing that'll tell you if this is true, then we have a normal subgroup. Another one is G capital H, where you have the whole subgroup is equal to H for all G in G. And then G, this is the one we've already been talking about. GH is equal to HG for all G in G. Again, if any of these are true, then we have a normal subgroup. So let's prove that these are really equivalent. And so we'll start by assuming this one and then prove that this is true. So in other words, we'll assume that that's true and prove that one's true. And actually what we'll end up doing, so like we'll do it this way for the proof. We'll start with one and prove that if you assume one is true, then that implies two is true. And then if two is true, that implies three is true. And if three is true, that implies one is true. So we're going to show that these are equivalent that way. So we'll start, so the first one, we'll assume one is true and prove two is true. So the one says GH, G inverse is in H for all G in G and H in H. So suppose H is a subgroup of G such that GHG inverse is in H. So we're assuming number one, this one right here, for all G and H in H. And then what does this mean? Then this means that GH G inverse is equal to GH G inverse such that H is in H. Now, what does this mean? Then this implies that this is going to be a subset of H. So this set here is going to be a subset of H. Because if we take GHG inverse, well, actually, we kind of have set it up here. We've said that this is in H, so then all these elements have to be in H. So then this is a subset of H. So if we want to prove number 2, remember, if you want to prove the 2 sets are equal, you have to prove that each is a subset of the other. So we're given this one, and this clearly is a subset of H. Now we have to prove the other way. So now show that G H G inverse is going to be equal, excuse me, it's going to be a subset. Excuse me, I want to say it the other way. Sorry. Now we want to show that H is a subset of GHG inverse. That's the next thing we want to show, because we have that this is a subset of this. So now we want to show that this is a subset of this. So let's go ahead and do this. So let H be an H. So in other words, I'm picking something on the left-hand side, and I ultimately want to show it's in the right-hand side. Then that'll prove that it's a subset. So in our equation up here, replace G with G inverse. So in other words, we're going back up to what we have here and replace G with G inverse. So that means this will be G inverse H G inverse inverse, which is certainly because this G and G inverse are both members of G, we can replace this with G inverse here. And then, of course, what is this going to be? Then that's going to be G inverse HG, again, which is a subset of H, because we set up here, these were all, well, excuse me, I should say, this is a member of H. Again, both of these are in G, so that's true. So let's give this a name. Let's call this H1. Just to, it'll be a little bit easier to work with. So what we have here, we have that H1 is equal to G inverse HG, like this. And then let's multiply on both sides. Let's multiply on the left by G. And let's multiply on the right by G inverse. And then, of course, this right here, this is going to be in GHG inverse. And now, of course, this is just the identity. This is the identity. So the right-hand side just becomes H. So GH1 is equal to H. And so now, since this was in GHG inverse, so H is in GHG inverse. Therefore, H is a subset of GHG inverse like this. Therefore, because up here we said that this was a subset of H, now we've shown it the other way around, that H is a subset of that. Therefore, we can say GHG inverse is equal to H. See if that makes sense. So again, the idea, let me pull this back a little bit here. So again, the idea is that we're assuming that this is true, and this H is from H. And it's from H, and then also this is a member of H. So this quantity right here is a member of H. So therefore, it's going to be this right here, and that's going to be the subset of H. So we proved that that was true this way. Then we had to prove, so we proved this is a subset of this. Next, we had to prove that this H is a subset of that, which we did. We picked a typical element in H and proved that it is in GHG inverse. And so we have them equivalent both ways. We showed that they're each subsets of each other. Therefore, we have GHG inverse equal to H. Any questions on that? So let's do the next one. So again, this is the way you usually prove these when they say that the following are equivalent, or these are all equivalent things. You assume this one and show it's this one. You can do it in different orders. You don't have to do it this way. Sometimes you might want to start with 3 and go to 1 and go to 2, whichever makes most sense. But main idea, you start with one of these, prove that if the one is true, it applies the other one. So now, so we assume 1 was true, we proved 2. Let's assume 2 is true and prove 3. So let's do that next. So suppose, so this one we're going to do 2 implies 3. So suppose GHG inverse is equal to H for all G in G. And now what we want to try to show is that this is true. So let's start this way. Let's let H be in where that let H be in H and G be in G. So let's do this. Let H be in H, G be in G. Then GHG inverse is going to be equal to H. I'll call it H1 again. This is not necessarily the same H1 from before, but let me just give it a number, call it H1. So we're assuming that this is true. Then if we take something in H and something in G, then GHG has got to be equal to some element in H. So this would be for some H1 in H. So now let's go here. Let's multiply. Let's see. Yeah, let me multiply on the right. Multiply on the right this time. Let me do G. So I multiplied on the right by G. Again, I'm working with both sides this time. And then this is going to be GH equals H1G. Now, this guy right here is in HG. So that means that GH is in HG. Because this one here, again, this one we said that this is going to be true for some H1 and H. Therefore, this is an HG. And since those are equal, this has to be an HG. So now we can, so what we did, we picked two typical elements here and proved that they were in HG. So therefore, we can say that GH is a subset of HG like this. So we have this to then next show that HG is a subset of GH. So we proved this was true. Now we've proved the other way, just like we always have to do if we want to prove two sets are equal. So let HG being capital HG then since GH G inverse is equal to H, that was, remember, that was what we're supposing. We're supposing 2 is true. So we're supposing that's true. And then since that's true, then let's see, G inverse H G is equal to H2 for some H2 in H. So let's see. So if this is true, then this is going to be true for some H2, H. In other words, of getting this from this step here. And then, once again, if we multiply on the left on each of these, G inverse HG, GH2, and then again, that's the identity. So this is going to be just HG is equal to GH2. But of course, this is going to be in GH. So see what we did? We picked. By the way, let me just. I realized I think I wrote this wrong here. Yeah, sorry. This doesn't look right. Could you please, let's see, oh, that's right, that's right. I think it's something different. Sorry, everything's okay. Yeah, so then This is in GH. So that means we've picked a typical element in HG. This would be a typical element in HG and proved that that element is equal to something in GH. So that means that HG is a subset of GH. And therefore, we had GH is a subset of HG, and HG is a subset of GH. Therefore, GH is equal to HG. Any questions on that? So finally, the last one, we're going to assume that 3 is true and prove that if 3 is true, 1 has got to be true. Then we will have completed the cycle. So this time we're going to assume 3 is true, prove that implies 1. So suppose HG, let me write it just so it's consistent with the way I did it before. Let me just write it this way. It doesn't really matter, but let me just put it. Suppose GH is equal to HG. That's from number 3. We're going to assume number 3 and show this is true. Then let H be in H and G be in G. Then GH is going to be equal, since this is true, GH is going to be equal to H1G for some H1 in H. Of course, I probably mentioned now notice what we're doing here is we can't necessarily assume that GH is equal to HG. We just know if this is true, there's going to be, if we have GH, there's going to be some H here that it's going to be equal to GH. It won't necessarily be the same H. That's why I've always been putting a different number here, because we can't necessarily assume that this, if the group is abelian, then it would, in things commuted, then it would be true that GH would be equal to HG. But the most we can say when we have this, if it's not abelian, we can just say that GH is equal to some H, what I call it H1G. Then we can say let's see, we'll multiply on the left, I guess, would be the most logical thing. So I'm just multiplying on the left here. Then this is going to be GHG. That's going to be the identity. That's this. Then since H1 is in H, we have GHG G inverse is in H, which was what number 1 was. That's what we're trying to prove for number 1, that G inverse was in H. So we just picked a typical H, a typical G, and prove that was in H. So take a look at all those. And see if you have any questions on any of that. Any questions on any of that? Okay. Okay, so now before I told you that these normal subgroups did in fact form a group, but we didn't actually prove that, so we'll prove this. Again, that's what I stated before. This is a theorem. And it's a little bit easier to prove it once we had gone through those equivalent ones. This is a little bit easier to prove this time. The cosets of a normal subgroup form a group. So let's go ahead and prove that. Again, we stated it before, now prove it. So let H be a normal subgroup of a group G. Then, by the previous theorem, we can say G inverse HG is equal to H from that stuff we just showed. So now let A and B and G, and H1, H2, B and H. Then, obviously, AH1 is in AH, and BH2 is in BH, and then AH1, BH2, and then I'm sorry, this was A. I wanted to put the identity between A and H1. Sorry, make this A H1 B H2. So I just threw the identity right in here. I think this is what we're going to end up wanting. And so then we can replace the identity here with B inverse H1 B H2. And then this is going to be equal, let's rearrange this a little bit, B inverse H1 B H2 And now, this right here, since A and B were from G, then we can say that this is in H. Because that was, remember, that was our assumption here. We're using that property, this property right here, that G inverse HG is equal to G. So then this has to be in H. Then this is going to be equal to, and let's call that, let me give this a name now. Maybe let's call this, let me hope this is, if you follow, let's call this H3 now. So it's going to be some H3 and H. So AB, H3, H2, like this. And then this is going to be equal to, now, let me first say this. Of course, this is obviously an H, like this. And then this is going to be, and maybe call this maybe H4. So then we're going to have AB, H4, like this. And that's going to be in ABH. Remember, that was the operation that we defined for these for this subgroup. If you took AB, if you took like AH, BH, you would end up with like ABH, where this was some member of H. So we have this. And also, we picked two elements from two different cosets. And prove their product was in in the group, was in another coset. And as a, so we have, so therefore it's closed. So we have closure. And then also, as I said before, H is going to be the identity for the group. And then also we're going to need an inverse. So let's take a look at this. So let me say H is the identity. Then for any AH, A inverse H is the inverse. Since A inverse H is equal to A inverse H, that's going to be equal to H. So if you want to find like what the inverse of any of the elements are, you can pick what the inverse would be in the original group. So if you have AH, its inverse in the original group is going to be A inverse. And because we have this operation that we just showed here, that we were able to multiply these and get AB here, then obviously if we're allowed to do, if we prove that this was true, then of course this is just going to be the identity, and that's just going to be H. So that's going to give us the inverse. So we have an inverse. And again, associativity, it's going to come from the fact that G is associative. Because you'll end up operating on those same elements. Let me say it this way. So these cosets. Any questions on any of that?
Why don't we say that just E is the identity? Why don't we say that H is the identity?
Oh, so in our in these cosets, since let me look at say this here. So for example, now we're dealing with these cosets as kind of an odd thing. These become the members. These are the members of our group rather than like say just numbers. And so therefore, they like say here, like say this was a particular group of cosets. And so in this case here, the members of the group are 5Z, 1 plus 5Z, 2 plus 5Z, etc. These are the 5 members. And so now the members of the group aren't the individual numbers, but it's these whole sets. So these 5 sets become the 5 members of the group. Then one of those has to be the inverse. So it has to be like a whole coset, if that makes sense. Any other questions on that? So again, this is called a factor group. A lot of times they call it a quotient group. And okay, so let's do a couple more things here real quickly. Almost out of time. Yeah, so let me just do this here. Another definition of an automorphism. So an isomorphism from a group to itself is called an automorphism. And so we're going to be working with those.